Hello. Now that we've had the chance to talk about ideal gases and the kinetic molecular theory that we can use to help describe them and understand what's going on a microscopic level, let's talk now about non-ideal gases, what we call so-called real gases. Gases where we actually take into account the fact that our assumptions break down and things are not going to follow exactly the ideal gas law. And so just as a reminder, we need to worry about real gas situations in things where we have high pressure or low temperature. Things where the gas is going to start behaving more and more like a liquid as gas particles start to clump together through attractive forces. So these are the situations where real gases, where we need to think about the things that we're going to talk about in this section. Now, one way to keep track of what's going on with real gases is, we have the ideal gas law, PV equals nRT, and one way we can reorganize this is to say, well, let's divide everything, right? If we divide PV by nRT, if we have an ideal gas, that should equal 1, just by definition of ideal gas law. And we call this factor on the left, we can combine the V and N here, right, and call that the molar volume, and we say this is PV bar over RT, and we call this Z, which is the compressibility factor. And this gives us a way to sort of judge whether a gas is behaving ideally or not. So if we can calculate the compressibility factor for as a function of different things and see how it behaves. And so we would expect at high temperatures and low pressures, Z should be about equal to 1 for things that are behaving like an ideal gas, and we should expect deviations from that if we're getting non-ideal behavior. So let's actually look at some data that I've pulled off of the internet. So on the left, we have a plot for nitrogen. This is a plot of Z, the compressibility factor, as a function of pressure in bar. And so when we're talking about low pressures on this plot here, that's like just this region over here, right, at around 1 bar. And you can see at around 1 bar, if we look up here, everything is pretty close to 1, if not exactly 1. Now the dashed line here, this represents ideal behavior. And the other lines that we see here are for different temperatures. So again, we should expect at higher temperatures, this should stay close to 1, and it does. At 400 Kelvin, not that high of a temperature, but for nitrogen, it's fairly high, a little bit above room temperature. We can see this red line on the top does stay pretty close to 1. Whereas at significantly lower temperatures, so 100 Kelvin, for example, right here, which I'll highlight in blue, we see very significant deviations from 1, even at fairly moderate pressures. So if you are familiar with nitrogen, the boiling point of nitrogen is 77 Kelvin. So this is only about a little over 20 degrees above liquid nitrogen's boiling point. So we're really close to the nitrogen starting to behave as a liquid, and so we see these very large deviations as we increase the pressure. And then that becomes lessened as we go to 160 Kelvin, and then up top, like I mentioned before, once we get to 400 Kelvin, it's much closer to ideal behavior. So that's looking at one gas and changing temperatures and pressures. The other thing we can do is look at different types of gases. So on the right figure I have over here, we have several different kinds of gases. Nitrogen is on here again as well. But we also have things like methane, hydrogen, oxygen, carbon dioxide. And we can see that we have, if all of these are at the same temperature, I don't have the temperature listed on here, so I assume it's room temperature, we see very different behavior for these gases as we increase the pressure. And here the pressure is in atmospheres. So carbon dioxide has the biggest deviation here, whereas nitrogen stays fairly close to 1. Hydrogen never decreases and goes up. So we can see in a real gas, as we get to, again, looking at fairly high pressures here for both of these cases, when we're at the low pressure limit, right over here, everything starts at 1, And then as we increase the pressure to pretty high levels, that's when we see this deviation from ideal behavior. So one question to think about, and I won't give you the answer in these videos, is why does Z decrease right? Why is it that it goes below 1 for any of these gases? The one exception is hydrogen. Everything else, as we increase the pressure, and I guess nitrogen at higher temperatures, why does Z decrease? I'll just put at lower temperatures. What's causing that behavior? So something for you to think about. I'd like you to answer that. Maybe write down your answer in your notes, and we'll also discuss it in class.